Hello everyone. In this video we are going to talk about context-free grammars, context-free languages. This is the first video about context-free languages. So far we have learned about a set of languages which we call them regular languages, but we know that not all languages are regular. So what would happen to the rest of the languages, something out of the regular language set? Is it possible to write down some machine to recognize those kind of languages? Is there some other actually set of languages that we can define in the hierarchy? And the answer is yes. Remember this hierarchy, the Chomsky hierarchy from the first week? We have talked about the regular languages, the smallest subset, and now we are going to switch to context-free languages. As you can see in this hierarchy, it actually shows regular languages is a subset of context-free languages. So everything which is a regular language is also a context-free language. All of these different sets that we have, they are not disjoint. They're creating a form of a hierarchy. They are supersets of each other. So the focus of almost the rest of the whole class is going to be the context-free languages. If I'm going to actually give you some intuition about the context-free languages, this is going to be the set of languages or problems that we can write them using a context-free grammar. I know you don't know what is context-free grammar. We are going to go through it, but just think about it as a grammar, as a set of rules, that these rules have recursive structures. So if you have some sort of recursive structure in your language, you can write down recursive form for that. So it's going to be a context-free. There are plenty of applications for context-free languages and grammars. Basically, the modern compilers, the advanced programming languages that we have, they are, the simplest form of them is context-free languages. So, for example, I shouldn't say that C or Java are context-free languages because they are not context-free exactly, but except some specific properties of them, the rest of the language is a context-free language, and you can write down a context-free grammar for that. This is something that's usually discussed in the in compiler topics, but anyway, you should. I just wanted you to know that. And all markup languages like the XML, XHTML, all of them are some context-free languages, and we can write some context-free grammar for them. So there is a very close relationship between compilers, parser that we wrote for the compilers for the languages, and the context-free grammars. So let's start our discussion by seeing a very simple example from context-free languages. Remember this problem, the problem of palindrome, binary palindromes? What is a palindrome? Any word that you read it from left to right or right to left in the same way, it is going to be palindrome. So all of these phrases are palindromes. And if your if your alphabet is binary, so we are going to, if a string is a binary palindrome, this is going to be this language that we are going to discuss. We know that this is not regular. We have seen, we can easily prove it using a pumping lemma, finding a string which is palindrome, then by actually just trying to pump it, for example, for once or twice, we will see that the result is not going to be in the language anymore. So this is not going to be a regular language. So what is this language? This language is in fact context-free language. This is not regular, but it is context-free language. And why it is a context-free language? Because we can write down a context-free grammar for that. And this is the context-free grammar that we wrote for it. As you can see, the context-free grammar is going to consist of a set of rules. Each of these lines is going to be a rule. It has a specific format. I'm going to give you the formal definition at the end. So this is just an example. I thought the best way to explain it is using an example. As you can see, each of these rules that we call them the set of productions in our grammar has a specific format that it has it is using actually this notation here, this arrow that shows you that something actually goes to something else. In fact, this is called the left-hand side, and this is called the right-hand side of the rule. Each of these lines is going to be a rule, and it has two parts, left-hand side and right-hand side. So we call this kind of grammars context-free because on the left-hand side, you can only have one token, and that token is going to be a variable. We call it a variable. And we also have non-terminals. You can see that on the right-hand side, you can have any form of a string, actually. So there is no restriction on the right-hand side. There is a restriction on the left-hand side. It should be exactly one variable, or sometimes we call it non-terminal. But on the right-hand side, you can have any string of terminal and non-terminals. Terminals are going to be all the characters from the alphabet, including epsilon. I mean, not only the alphabet, but also the epsilon. And you can create any form of strings, which is a combination, a sequence of terminal and non-terminal, like this one, or for example, this one. Okay, and so how we, let me just give you an example that, for example, how can I create a string, a simple string like this using this grammar? I will use this rule, and it actually from A, I started actually from some variable. And here I only have one variable A, so you start from the variable A, and using this rule from A you can reach to this substring. You see that this is not a string from the language, because you have some token which is not a part of the alphabet, right? So I will continue, replace that. Again, instead of this variable A here, I can use this rule, and you can see that I always actually pick some variable, and instead of and then using one of the rules, I put the right hand side of one rule instead of that variable. I mean, I will substitute it with that variable. So this A has been replaced with 1A1. Still I have a variable A, and then I'm going to use this rule and replace A with the right hand side of this rule. So at the end it gives me a string from the language. All of the token symbols in this sequence that you can see is a part of the alphabet, and it is a string from the language. If I just wanted to give you an informal definition of context-free languages, any language that you can write a context-free grammar for that, it is going to be a context-free language. What is a context-free grammar? I'm going to give you the formal definition later, but just an informal definition is that it's going to be a set of rules that using those rules I can generate some strings. So be careful about the the grammar and for example in regular languages we had automaton. Grammar for the context-free grammar is like the relationship that the regular expression had for the regular languages. So grammar is a representation for the language. Grammar just tells us how the strings in the language will be generated. Okay, so it doesn't actually tell us if we accept. This is not a machine, so it is not going to be an automaton, but it is going to represent, it's going to tell me how the strings will be generated. And so if a grammar represents a language, it means that all the strings in the language should be generated using this grammar, and all the strings that can be generated using the grammar are in the language. Okay, so it's going to be exactly the complete representation. So one more notation here is that, as you can see, I have 5 rules in this grammar. I can actually write them, kind of shorten it and write it in some other way, like this box here. So these are actually telling me that there is going to be 5 different rules, but all of them have the same left hand side. I just separated all different rules here by using the pipe character. Okay, it is just the shortened way to write down the same grammar instead of writing it in different lines. So let's just actually go back to this question, that how a grammar generates a string or derive a string. Sometimes we call it a derive. Many times we call it a derive a string. This example that I showed you, this string, which is palindrome and can be generated using this grammar, of course. These 3 different steps that we wrote here is exactly telling me that how the string can be generated using the grammar. And if a string can be generated using this grammar, it should be in the language of the corresponding grammar. So informally, again, the thing is, we usually actually have a variable that we call it the starting variable. You start from that starting variable. In this example, we just had 1 variable, and so that's going to be a starting as well, which is the variable a. You start from 1 variable, and each time you pick a rule and replace the variable with the right hand side of the rule, and you continue until there is no variable in the sequence. Okay, in that case you reach to a string which belongs to the language, and you have, this is how we generate a string. So you can see that you can actually use different rules. We have different rules, and that's why by combining these rules you can generate different strings. For example, if at first I used another rule, for example, a goes to 1A1, and then actually just continue replace a with the second rule 1A11, replace it with the last rule. It is going to give me one epsilon 1 and this is just like epsilon will be vanished, so 111 is the final string, right? This is going to be a string in the language which is a palindrome, right? You can have any combination of these rules. There is no restriction on that. So if you have a set of rules, you can use them in any order as you want, and all the strings that can be generated are in the language. So now let's look at the formal definition of the context-free grammars. Context-free grammars will be defined using a four tuple, V, T, P, and S. Usually we actually just show it as a G. The grammar G has four different parts. V is the set of variables or non-terminals. T is the set of terminals, that this is going to be the set of all the tokens in the alphabet, and including the epsilon. Epsilon is also epsilon is not a part of any alphabet actually, but it is a part of the terminal in any context-free grammar. This is going to be a terminal token. And be careful, their intersection between the variables and terminals should be empty. You cannot have one symbol which is in the terminal and it is also in the variables as well. Usually we use capital characters, capital letters to show the variables. So kind of it actually just shows you that these are variables and they're going to be more recognizable. Or for example, if this is not just one symbol, it can be a larger string. It can be a complete string. Any string can be used as a variable. It doesn't really matter. And we have a set of rules that we call it production P. All the rules are in this format. We have a left-hand side and the right-hand side. As you can see, the left-hand side, this is a part of the rule. This is a restriction over the context-free grammars that tells you that left-hand side should be one variable, one single variable. But the right-hand side can be any arbitrary sequence of variables and terminals. And we are going to have one starting symbol. The starting symbol is going to be a variable. And it actually tells us from which variable you can start generating the strings, the words in the language. And be careful, again, I'm emphasizing that the string in the language should only have terminals, should only have the alphabet from some token from the alphabet. If you stop somewhere, for example, in this example, this is not a string in the language. You have to continue and replace A and get rid of all the variables. Otherwise, you are not going to get a string in the language. This is still like a this is a substring or a derivation, sometimes we call it. Okay, so this is an example. The previous grammar that we have seen, we can write it in this way, that the set of variables was just one variable, the terminal set, the alphabet actually, some production rules, which I wrote it here, and the starting variable, which is A. In fact, all of the discussion that we had for the regular languages, we are going to have for the context-free grammars as well. We are going to talk about the machine, the type of machine or automaton that can recognize context-free languages. This is called push-down automata. Like the deterministic automata, non-deterministic finite state automata, non-deterministic finite state automata. For the regular languages here, the machine is called push-down automata. This is not a finite state machine anymore. This is called push-down automata. So this is something that we are going to discuss about it. We will discuss about context-free grammar. We will see many examples of this. This is the kind of a descriptor for the context-free languages, like the expression, regular expression for regular languages. We will discuss about the pumping lemma for the context-free languages. So there is some property which is called the pumping property for the context-free languages as well. So if a language is a context-free language, this theory should be, should hold for that. This property should hold for that. We will talk about the closure properties for context-free grammars and different operations. Discuss that if the context-free languages are closed under different operations or no. And we also discussed about the decision problems that we can answer on context-free languages. So kind of you will see that there is a quite close relationship between the context-free grammars, and regular languages in terms of, all the topics that we discussed. But there is one main difference, just in terms of this analogy, that in regular languages, remember we always said that non-deterministic finite automata or deterministic finite automata have the same power. Any non-deterministic finite automata can be converted to a deterministic finite automata. And any deterministic one is, in fact, a non-deterministic. So they are going to represent exactly the same set and they have the same power. Here, for the push-down automata is going to be the machine. Automaton is going to be the machine that accepts regular languages, the context-free languages. And there are, again, two different types of push-down automata, non-deterministic push-down automata and deterministic push-down automata. But deterministic and non-deterministic push-down automata are not going to be equivalent. Non-deterministic ones are going to have more power. So, in fact, deterministic push-down automata is going to represent a subset of context-free languages, not all context-free languages. So it's just like the non-deterministic ones have more power. They are going to represent the whole set of context-free languages, but deterministic ones are going to create a subset of the context-free languages. We cannot create a deterministic PDA, or push-down automata, for every context-free language. This is something that we come back to it later when we discussed about the PDAs. So let's see more example. Remember this language from our discussion about regular languages? This was the very first example that we saw. This language is not regular. So is it context-free or no? If it is context-free, it means that we have to be able to write a context-free grammar for it. If you want to prove something is context-free grammar, you should be able to write a grammar for that, or you should show you can create a push-down automata for that. We don't know about the push-down automata, so I'm going to try to write down a context-free grammar for it. So this is the set of strings that has a number of zeros followed by exactly the same number of ones. How to write a grammar for this? I am going to write a grammar for this starting from some variable and say that, okay, I need some rule to generate zeros and ones, right? I need some rule to give me the 0 and 1. I'm going to be able to generate all the strings. So, for example, I need a rule that actually generate 1, 0, 1. And I need a rule that generates, for example, 0, 0, 1, 1, right? If you actually write it down, it's going to have infinite number of rules, right? So this is not going to actually work. I cannot write the grammar in this way. So I need to reuse the variables. So whenever you are trying to write a context-free grammar, try to think about some recursive structure. This is going to help you to write the grammar for that. Whenever you find some recursive structure, so it means that something is going to be repeated. Okay, I wanted to actually be able to find some way to repeat this variable and use one rule to just repeatedly generate and give me longer and longer and longer rules. So I can think of these larger strings that I have in this way, that this larger string, this one here, has been generated by putting, in fact this is the previous string, right, by actually adding some more 0 and 1, outside of that, to the left of it and to the right of it. If you think about this one, you can see that again, this one is something that has been generated from the previous one by just putting the 0, 1. So this is exactly the format that I need to think about. So something like this rule, if I have, I have some, this is just exactly finding some recursive relation. Find some base and some recursive rule. The recursive rule that I just actually discovered is this rule, that just by putting some 0 and 1 and repeatedly using this rule, I can generate longer and longer and longer strings. I also need some base case. I need some time to get rid of this variable. How can I get rid of the variable? By just going to epsilon, right? Then the variable is going to be gone. That's it. I'm done with writing a grammar for this language. So you just need to be able to think about the problems in a recursive format. Find some recursive structure for your strings in the language and try to write down those recursive structure as some rule, as a set of rules. So let's see another example. I'm going to write down a grammar for this language. Okay, so the thing is, this is a context-free language. If I gave you some example, maybe some examples I gave you, they are not going to be context-free languages. So, sorry, you cannot write the grammar for them. So far we are going to work on simpler examples, but later on we will see some examples that the language is not a context-free language. We cannot write a context-free grammar for that. But this one is. What is the language? The language is a form of, I called it balanced binary strings, similar to balanced parentheses. In a way that, for example, 0 corresponds to left parenthesis and 1 corresponds to right parenthesis. So in this way, a balanced binary string. So 0, 1, this is something like the open and close parentheses. This is balanced, right? Or for example, this one, some nested open, some nested parentheses. This is going to be a valid balanced binary string, right? Or this one that is the a concatenation of two other balanced binary string. What do you think about this? We need to find some recursive relationships to generate these strings, and also find some actually base cases for those recursion as well. One thing that so far in these examples you have seen is that we can generate larger and larger, longer and longer strings by allowing the nested parentheses, right? So one thing is the strings can be generated in this format, the nested balanced parentheses, or it can be generated by the concatenation of two other balanced string. So that's enough. That's going to cover all the balanced binary strings, or all the balanced parentheses if the language is balanced parentheses. So I have two rules. The first one is allowing me to create some nested so this 0 1, as you can see, this is going to give me that nested structure recursively using that. And the other one is the concatenation of two balanced string. So it's just like you think about A as a variable which is going to give me a balanced string. I'm going to, what is the recursive structure for that? Either it is going to give me through some nested rules like this one, or through some concatenation. You can see that I wrote it as AA, but it doesn't mean that you have to use the same rule for A and A. I will actually just show you some example later, but these are the two rules that I need. And I also need some base case, right? I need to stop at some point. So I'm going to add one more rule that A goes to epsilon. Or if the, I don't, depends on what is in the language. If the epsilon is in the language, this is going to be enough. If the epsilon, you exclude it from the language, you can write the grammar in this form. That's 0, A1, AA, or just 0, 1. Okay, instead of epsilon, I just gave it as 0, 1. But I think in the example that, in the solution that I wrote, yes, I consider that epsilon is in the language. So that's it. But be careful, when you see a format like this, it doesn't mean that you have to exactly give the same, replace the same string for A and A. It's just telling you that you can, A has been generated, the string has been generated by concatenating two other strings that can be generated using the same variable. So let me just show you a derivation, how we actually can generate a string like this. This is a balanced, I don't know if it is or not, but let's actually just see that if it is in the language or no. This is going to be something like, when I write it as a parenthesis, it makes more sense to me. When I just look it as a 0 and 1s, it doesn't really. And okay, now you can see that this is balanced, right? Yes, this is in the language. Now let's see that how we can generate this string using this grammar. So I'm going to start from the starting variable is A. From A, so by looking at the string, it is actually, you can see that it has some, by looking at this, you can see that this 0 and 1 are corresponding to each other. So if I'm going to generate this string, I have to use the first rule, and then I have this set here. I should be able to actually generate this one, so I will continue. Not only this one, this is, I also need to actually generate this. So I'm going to use the second rule, AA, and then for this one, continue and generate this nested, three nested 0 1s. So 0, A1, 0, A1, 0, A1, and this one goes to epsilon. Just disappear. I just forgot that right now I am drawing a parse tree for you. So let's see how we can generate a string like this using this grammar. I will start from A, then I am going to use the first rule, then I will use the second rule, then I can use, I'm going to replace, you can see that I have two variables. I should replace both of them. I'm going to start from the left one. I'm going to use the first variable, first rule. And I'm going to use that rule for 2 more times. And I'm going to get rid of this variable with epsilon. You can see that it's actually giving me this part of the string. So I'm going to replace it with epsilon. They're using the last rule. I don't write it down, so I just get rid of that. I think I accidentally added one more variable, 1. Okay, and then I am going to use replace this variable with the second rule. A1, and I'm going to replace the first one with the first rule, and then I'm going to get rid of this one using the last rule, epsilon. So I'm not writing the epsilon, but okay, now this one. I'm going to use the first rule again. And then replace the A with epsilon again, and just get rid of all the variables. 1, 1, 1, 0, 1, 0, 1, 1. This is exactly the string that I had, right? So you might actually have already noticed that there are different ways to generate this string by applying the rules. But it doesn't matter which one you use, which way you find. If you find a way to generate the string, so that's it, the string is in the language. Otherwise, the string is not in the language. So let's do another example. The set of all the strings, 0, 1, binary strings, that it has a couple of zeros and followed by some ones, which the number of zeros are greater than or equal to the number of ones. So one thing about this grammar is, first, this is not regular. Remember, I think we had it in the exercise set, or I proved it in the slides, but anyway, this is not regular, again, because it has some kind of, actually, it needs to remember how many number of zeros it has to make sure it has greater, the number of ones is less than that. So to be able to write a grammar for that, I need to find some recursive structure again. So what is the recursive structure to give me a couple of zeros followed by 1 and tell me that the number of zeros are greater than the number of ones? I can try to divide this to 2 steps. First, I would say that let's just create the, for whatever string in this language, I can say that it can be generated in two phases. The first phase is to generate as many number of zeros and ones, I mean the equal number of 0 and 1. And then in the second step, just add as many number of 0 as you like. Okay? So I can write down one rule for the first step. So first phase, generate equal number of zeros and ones. So it's just kind of generate a part of the string that has equal number of zeros and ones. That has equal, that has this format, sorry. Phase 2. Add more zeros if you need. Okay, so we already know how to write a grammar for this one. How to write a recursive structure for that. So let's just like, I am going to generate some zeros followed by some ones, right? And then whenever you are done with this recursion, this recursively generates equal number of zeros followed by equal number of ones, then we are going to actually just move to the second phase. So the second phase is generating, you can actually write it using more variables. I'm going to use more variable here to make it more clear for you that what's happening. But you can actually say that move to another variable. And this variable is supposed, this variable B is supposed to actually do the second phase. That generate as many number of zeros. And you can see that how I am actually writing this. You will generate equal number of zeros and ones in this phase, and then whenever you move to B, you never actually go back to A. You can go back to A as well, but you don't need to. I mean, that's just the case. And also just disappear, go to epsilon. Okay, so I wrote it down using two different phases, and for each one I found some actually recursive structure. This recursive structure and this recursive structure. The answer that I wrote here for you is this one, which is I wrote it using just one variable. And one thing about writing it using one variable or two variable is that when you are writing it using one variable, you should be careful that where you put this 0. You should always put it in the left of it. So the number of zeros are going to be, if you interchangeably using this rule or this rule, always the number of zeros are going to be adjacent. All the zeros are going to be adjacent. In the previous example that I gave you, instead of 0b, I could even write it as b0 as well. There was no difference between these two. But when you are writing it using one variable, you should be careful that you always put 0 on the left-hand side of A, so that all zeros are going to be adjacent at the end. But again, just as an example, let's try to generate this string here. Using this grammar that I have. Let me just erase this. Using this grammar, I can just do it in two phases. Exactly, try to actually generate 3 number of zeros followed by 3 number of ones. 0, a 1. Again, use the first part of the rule, using the first part of the rule, and then I started generating the zeros. The second part of the, and then I need one more 0. And then use the epsilon to replace a and get a complete string. Yes. Another example, I'm trying to write down some context-free grammar for a very simple kind of language which consists of 2 different type of statements. If then else or if then. So this is one format and this is one format. So here just assume that, I mean, for us the tokens, the terminals are going to be if, then, and else. Okay, this condition and a statement, you can just consider them as some other variables that condition has its own rule to generate a condition, and a statement has its own rule to generate a statement. So that's why I'm going to represent a condition using a variable like C and a statement using a variable, let's just call it S. How to write a grammar for this? I should basically think about some recursive, again, structure. This is something similar to the nested parentheses or balanced parentheses, right? You have either nested or the concatenation of 2 other a statement or 2 other strings which are balanced. So if I wanted to write a grammar for this, this is going to have one rule for allowing, the sequential if statements, the concatenation of some if statement, and the other one is some rule like if, some condition, then some statement. So this way you can do it in a nested format. And I need another rule for the other form of the if statement, if, some condition, then some statement, else, again another statement. Okay, that you can have it nested format in both of these 2. And I'm not writing it down that how the condition has been generated, or the statements can be generated in some other format as well. This example was just emphasizing on the part that have if then else statements. Okay, I forgot that epsilon as well, that how to actually get rid of the statements. In fact, when we are talking about context-free grammars, we are talking about compilers. Compilers for the programming languages are a kind of a machine that takes a program and check that if it is this language, if your input, which is your source code, is a valid language, is a valid sentence, is a valid sentence or a string in the language of all the valid languages of C or C++ or Java or something like that. Okay, not only that, it also creates a parse tree and then execute it on the computer as well, but those parts are not about the compilation. If there is any syntax error in your program, basically means that you have written some string which is not in the language. It is not in the language of all the valid C++ program or all the valid Java programs. All right, and the compiler try to actually check that if your source code is in the language, and if not, gives you the syntax error. So whenever you have a syntax error, compiler actually just try to check the validity and check that if it can be generated using some grammar. So basically all these programming languages, Java, C++, Python, everything, they have a set of rules that allows us to generate any program that we wrote should follow those rules. Any program that we wrote actually has been generated using that set of rules. For example, you have a set of rules for the balanced parentheses, you have a set of rules for generating the loops, you have a set of rules to generate the if statements, you have a set of rules to generate arithmetic expressions. The rules for a compiler, for a complete programming language, advanced programming language, are very, it is going to be a large set of rules. In a compiler course, if you take a compiler course, in that course usually one of the projects that will be done is writing a complete grammar for a given programming language, usually a simplified version of the advanced programming language. So context-free grammars not only are, I should say that in fact context-free grammars has been invented not for the sake of computer science and not for the sake of writing advanced programming languages, but they have been invented in linguistic area. Noam Chomsky invented context-free languages for the first time, and although Chomsky is a well-known name in politics, in many different fields, but he was first a linguist. He invented context-free languages to be able to kind of find some structure for natural languages. Although at the end linguists end up to this that it's not possible to write down any grammar, not only context-free, it's not possible to write down a complete grammar for a natural language, but in 1970s, people started using context-free grammars to write down some languages for computers. And this is when we started actually using context-free grammars, not for the natural languages, but for the programming languages. This example that I am showing you here is just a very simple set of rules that tries to capture some form of generating a sentence for the natural languages. For example, any sentence you can think of as a sentence in English as a combination, as a noun phrase and then a verb phrase. Then you can actually write down some rule for the noun phrase, how you generate a noun phrase, how you generate a verb phrase. For the noun phrase, you can see that all of these tokens between the less than or equal, these symbols are going to be a non-terminal, a variable, and the terminals are going to be some valid words in English. For example, these are some names, these are some determiner, some verbs, right? This set of rules definitely are not complete, but it is just trying to tell you that where the context-free grammars actually came from. Using this set of rules, I can generate some simple sentences like, for example, sentence goes to noun phrase, verb phrase, then noun phrase goes to proper noun using this rule, and proper noun go to, for example, it can goes to some terminal like Jill. And then verb phrase can be actually replaced with this rule, verb and adverb, where verb goes to derives this rule, and adverb goes to, for example, frequently. So Jill derives frequently. This is a sentence, this is a valid sentence in English, right? And it can be generated using these rules. Not only these rules are not enough to generate all sentences in English, but also they can generate very, ambiguous and something that's semantically wrong sentences. For example, Jill eats car. This is something that can be generated using this set of rules. But this is not in the, this is semantically wrong, right? So no one writes some sentence like this in English. And this is because natural languages are very ambiguous. You cannot write down a complete set of rules to generate all the valid English sentences and only valid English sentences, or any other natural languages. I just wanted to actually tell you about the origin of context-free grammars and where they came from. So I'm going to give you a couple of different notations and definitions, which we need them and we refer to them a lot when we talk about context-free grammars. The first one is derivation. I have actually referred to this word a lot so far. So the question is how we say a string belongs to a language. This is, one of the main questions that we have. So there are two different ways to check if a string belongs to a language. One of them is trying to actually create a derivation for the string. This is exactly what we did in the previous examples. Like, for example, here, I just showed you a derivation, how I started from this variable a and I ended up to this string. Okay, this is called derivation, that you started from some variable and you try to find the set of a sequence of applying different rules and you generate the string. The other way to do it is you just do the same process in a reverse format. Instead of starting from one variable and just find the set of rules that you need, the sequence of rules that you need to apply to generate the string, you can get the string and started to just do some kind of reverse engineering. So instead of doing the derivation in a just like top-down manner, you do it in a bottom-up manner. You start from the string and think that, okay, how can I, for this part of it can be replaced with the variable a using this rule, and then this part can be replaced with variable a again using this rule, right? And this part can be replaced with a variable a using this rule. So just the reverse format of that. It doesn't matter which way you go. If you find both of these two different approach, just try to tell you how we are generating the string using this grammar. So we know that the string belongs to the language. How we write the notation of the derivation. Just one step of derivation can be written in this format, that the left hand side is a variable. You use this symbol, this simple arrow that goes to another string, which this string is going to be, this is going to be one rule in your this is going to be one step in your derivation. So for example here, a goes to 0, a 0. Okay, I can extend this one step and say that if you started from a sequence And after applying a couple of rules and actually replacing some variable in this string, as I wrote it, this is not a one variable, it can be any string. After applying a couple of steps of the rules, if you reach to x, we say that from A, we derive x, or A derives x using some rules from the grammar G. This is just the extended format of this one step. Okay, so for example, something like this, that 0A1 after, just assume, or in this grammar, 0A0 can go to can derive this string, right? It just from this, after applying a couple of rules, you can reach to this. I just, replaced all of those steps using this notation that it shows me that I have applied the rules a couple of times. There is some properties for the generalized derivation, that if from A you can reach to B using the rules from grammar G, and from B you can actually derive C, it means that A can derive C as well. So it's kind of a transitivity property. So another definition here is, we defined a language of a variable in the context-free grammar to be all the strings that are just a sequence of terminals that can be generated using a variable in our grammar. So if you have more than one variable, for each of the variables, you can define the language for that specific variable. It doesn't mean that this is going to be the starting variable only. You can define it for any variable in your grammar. That's going to be the language of that variable. And the language of the starting variable is going to be equivalent to the language of the grammar, right? Because it's telling you, are actually saying that the set of all terminal strings which can be generated from the starting variable. It means that all the strings that can be generated using this grammar, because if you are going to generate a string, you have to start from using this grammar, you have to start from the starting variable, sorry. So this is the formal definition of a language for a context-free grammar. That if you have a context-free grammar like this, the language of this grammar, that we usually write it as L of G, is going to be the set of all terminals, the set of all sequences of terminals. You can say that this is just like an alphabet in the regular languages. The set of all valid, all strings of terminals, all sequences of terminals that can be derived from the starting state by applying any number of rules from the grammar. So let me actually give you another example, the set of simple expressions. So I'm going to write down some rules, some grammar for a language which is just some simple arithmetic expressions. I am actually restricting the integer numbers to be just only 0, 1, or the identifier to be just creating using these four characters. So I can write down, and all the operators that I have are just plus multiplication, and I can have the parentheses, open and close parentheses as well. Right? So I can write down some grammar for this, like these are the rules. Okay? That this is going to allow me any combination of, plus multiplication, some having some valid nested parentheses, and it's the identifier E is the variable which is, if E goes to I, you are going to replace it with some identifier. It can be just started from 1A or B and followed by some 0 or 1s. For example, A is a valid identifier, B is a valid identifier, AA is a valid identifier, A0 is a valid identifier, A00 is a valid identifier, and many more. Right? So these are just rules that we need to generate this set of arithmetic expressions. So let me actually just show you a couple of examples. For example, this one, and then using this example, I will give you two more definitions: what is leftmost derivation and what is rightmost. We call rightmost derivation. So let's look at this string and see that how can I generate this string. I'm going to write down some, find the derivation for this string, right? It started from S. Sorry, we don't have S here. It started from E. The starting symbol for us is E here. E goes to, you can see that I have this multiplication, so I need to use this rule. E multiplied by E. Then I am going to, now you can see that I have two options. I can try to actually expand this one, or replace this one or this one, the second one. Which one? Let's just stick to the left variable always in all of the derivations. So I'm going to replace E can be actually, I'm going to get A out of it. So I'm going to use the last rule, E go to I, and then I go to A. So I end up with one string that has one variable. Now E goes to open parentheses, E close parentheses. Then it goes to, I need to actually create this structure, right? E plus E. Again, I have two variables. I'm going to stick always to the left one. So I'm going to replace this with the identifier. So you can see that whenever I have more operator, I'm going to keep using some rules over E. And whenever I reach to one identifier, I need to move to using the rules for I. And then stick to the left variable always. So I'm going to replace I. Then E will be replaced. I need to generate another identifier. B plus, to generate B0, I need to use I0, and then this one will be B0, and then we are done. We got the string that we want. So you can see that in all of these cases, in all of these steps, I had different choices I mean, not all of them. In some of them, I had different, I mean, more than one choice. For example, this one or this one or this one. But I always stick to the leftmost variable in the derivation to expand. This is called leftmost derivation. If you always substitute the leftmost variable in your derivation, this is called leftmost derivation, and we usually actually just show it in this notation using the LM over the derivation notation. If you stick to the rightmost derivation, this is going to be called rightmost. I mean, if you stick to the rightmost variable to substitute, this is going to be the rightmost derivation, right? So this is rightmost and this is leftmost. You stick to the left or to the right variable. So usually when we are writing down the derivation, either we go with the leftmost derivation or to the rightmost derivation. It doesn't matter which one, it just depends on what you are doing. And so to just makes it more clear that the rules that you are applying, it is better to always just stick to one of these two formats. So now I have a question for you. I mean, I have 3 questions for you to think about. So now that you know about rightmost derivation and leftmost derivation, which are just 2 different formats to write down the set of rules and write down the complete derivation. Can we say, is it true or false, this statement? For every leftmost derivation, there is a rightmost derivation and vice versa. So it means that if you can write down a leftmost derivation, it means that you can also write down for a string. If there is a leftmost derivation, it means there is a rightmost derivation as well, and vice versa. Is it true or false? Think about it. I'm going to come back and answer all of these questions. The second question is, does every string, every word that in the language that can be generated using your context-free grammar have a leftmost derivation and a rightmost derivation or no? Is the answer for this question yes or no? And the last question is, are there any strings in any context-free grammar that can have more than one leftmost derivation or rightmost derivation or no? So think about these questions. I will come back and answer all of them. One more term that we use a lot in context-free grammars is parse tree. Parse tree is in fact some visual format of representing the derivation. So parse tree is not going to give you more power. It doesn't do anything else except writing down the derivation in a more visual format. So a parse tree and derivations and recursive inference, all of them are equivalent. I mean, if you have a parse tree, you can write down a derivation for that. If you have a derivation, it means that you can write down a recursive inference. If you have a recursive inference, from the recursive inference, you can create a parse tree. So all of these are just different formats, and they just represent how we generate a string in a language. You have a string, you want to know that if this string is generated by the grammar or no. If you can create a parse tree for that, it means it is in the language. It is generated by the grammar, right? And it means that from that parse tree, you can find the derivation for that string, and you can write down the recursive inference as well. And vice versa. It means that if you can find the derivation for a string, you can create a parse tree for that. If you can find a recursive inference, you can create a parse tree for that. There is an important fact about the parse trees that makes them more useful than derivations and inference and recursive inference, is that not only parse trees, if you can create a parse tree for a string, it means yes, the string can be generated using your grammar, but also it gives you some kind of interpretation from the string. Where this interpretation became important for us when we talk about some grammars, like the grammar for a programming language. In compilers, when you give a source code to a compiler, it not only needs to find any syntax error in your grammar, but also it needs to execute it, right? So compiler will create a parse tree from your program. First step to check the syntax, and then after that, that parse tree allows us to create an executive code, the code that you run on the computer. It's just, that is the interpretation from the program that we get. And not only just checking the syntax error, but also how to run that program on the computer. This interpretation, this is something that I come back to it when we talked about the ambiguous grammars. So let's write down the formal definition of a parse tree. I have talked about the parse trees a lot, but didn't give you the definition. We define a parse tree for a grammar, context-free grammar G, with 4 parts here, as a tree that all the nodes in the tree are going to be either terminal symbol or non-terminal symbol. With this restriction that the internal nodes in the tree have to be all variables, and the leaf nodes has to be all terminals. Okay, so it's just like when you read the leaf nodes from left to right, it gives you a valid string in the language. I mean, this is the definition. Still I have some other parts to say. The root node in your parse tree should be the starting state. And if you have any internal node with label A, remember the internal nodes, all of them should be variable. If you have an internal node with label A and with a set of children with labels x1 through xn, if it is the case in your tree, you should have a rule in your grammar in this format that the variable A goes to x1 through xn. This is the definition of the parse tree. I can extend this definition and define derivation tree. What is derivation tree? A derivation tree is in fact a parse tree without some restrictions. So the label of the root can be, instead of a starting state, it can be any variable. A starting variable, it can be any variable. So in this way, you can create a derivation tree. And not only that, the leaf nodes doesn't need to be all terminals. You can just have some leaf nodes which are non-terminal. Let me give you some example of derivation trees. So all of these are derivation trees. Some of them are parse tree. For example, this one is a parse tree, right? It starts, the root node is the starting variable, and all the leaf nodes are terminals. Okay, and how we actually read this parse tree is going to give me one string. It tells me that how a string has been generated, or you say that what this parse tree yield. This parse tree yield a string that you can get it by reading all the leaf nodes from left to right. So A, then plus, then 1. This is going to be the string that can be generated using this parse tree. These two are examples of derivation trees. These are not exactly parse tree because in this case, you can see that the root label is not the starting variable. And I also actually, in the leaf nodes, I am allowing to have non-terminals. What this derivation tree yield, again, I just read all the leaf nodes from the left to right. IA0, this is going to be the result, whatever has been generated using this derivation tree. In fact, you can see that this is just some representation, some visualization of those derivation. So for example, something like this, that I goes to I0, then IA0, right? These are two steps. These are just this is just a derivation, right? I'm just representing it using a tree. Or for example, this one is just a derivation tree that yield this string A plus E multiply E, and it is just a set of rules. This is just like you started from E, go to E plus E, then this one replaced by I, then this one replaced by A, then you actually continue and replace this one with E multiplied by E, and that's it. So all these steps, this full derivation has been represented using this tree. I just give it a visualization. So these are just the notes that about the derivation tree. And it tells us that if in the derivation tree we start from S, the result of the tree is going to actually give us some sentential form. What are the sentential form? This is just again another name. A sentential form is going to be any string, any sequence of terminal and non-terminal that can be derived from the starting set. So basically, this is just the derivation, then definition of the sentential form. So let's now actually go back about our discussion about the parse trees and derivations. One observation that we have while comparing derivations and parse trees is that every full derivation for a string can be actually represented using a parse tree. So every derivation can be represented using exactly one parse tree. Okay, so for example, this derivation here can be represented using this parse tree. But not all the parse trees, but each parse tree can represent different derivations. For example, the same parse tree here represent this derivation, represent this derivation, and represent this derivation. This one is a leftmost derivation, this one is a rightmost derivation, this one is just mixed. I just randomly choose which variable to expand in the derivation. But all of them have a unique parse tree. So it is one more interesting thing about property about the parse trees. One parse tree can represent a couple of different derivations. But it is interesting to know that one other observation that we can have here is that every parse tree that we have is going to represent exactly one leftmost derivation or rightmost derivation. So if you have one parse tree, it is corresponding to exactly one leftmost derivation and exactly one rightmost derivation. So all of those derivations that are going to be in fact the same, this is just the matter of changing the order of the rules that you are applying, is going to be represented using one tree. And so there is a unique parse tree and when you have a parse tree, there is a unique leftmost derivation and there is a unique rightmost derivation for that. And one more observation here that we can have is that depending on the grammar, there might be some strings that have more than one parse trees. It is possible depending on the grammar. So this is the property of the ambiguous grammars. If your grammar is ambiguous, there will be some strings that can have more than one parse tree. If you have more than one parse tree, it means that you have more than one leftmost derivation for your string as well. So by having all of these observations, I can go back and answer all those questions that I asked at first, a couple of minutes ago. The first question was this statement that we wanted to know that if it is true or false. For every leftmost derivation, there is a rightmost derivation and vice versa. Yes, this is true. This is exactly that observation that we had for the parse trees. If you have one parse tree, there is a unique leftmost derivation for that, and there is a unique rightmost derivation for that. So if there is a leftmost derivation, there is a rightmost derivation as well. The other question was, does every word generated by a grammar, a context-free grammar, have a leftmost derivation and a rightmost derivation? Yes, again, because the string can be generated using a grammar, it can be represented using a parse tree. If you can represent it using a parse tree, you can create a leftmost derivation for that, and you have a rightmost derivation as well. And the last question is that, could there be some word which have more than one leftmost derivation or rightmost derivation? And the answer here again is yes. It depends on the grammar. If the grammar is ambiguous, for some grammars are ambiguous. I'm going to discuss about it later. So there will be more than one parse tree for them. So there will be more than one leftmost derivation and more than one rightmost derivations. So in this slide, I'm just trying to rewrite all of those observations and properties that we have learned about parse trees, derivations, and recursive inference. All of these, parse tree, derivation, and recursive inference, are different representation of the same thing. How we can generate a string using a grammar. Or in other words, if a string belongs to a language or no. All of these three are representing exactly the same concept. How a string can be generated using a grammar. And all of them are equivalent. So I'm expanding the previous picture that I had. Parse tree, recursive inference, derivation, rightmost derivation, leftmost derivation, all of them are representing the same concept. All of them, for a string, if we have a derivation, we have a leftmost derivation, we can create a leftmost derivation, we can create a rightmost derivation, we can create a parse tree, we can write down a recursive inference. Okay, so all of them are equivalent. And how these rows that I actually write, that for example from derivation to recursive inference, from recursive inference to parse tree, it doesn't mean that you cannot from recursive inference go back to derivation, but it just shows you that how easily, which one is more easier. If you have a recursive inference, you can easily create a parse tree from that. If you have a parse tree, you can easily write down the leftmost derivation. You can easily write down the rightmost derivation. If you have a rightmost derivation, you have a derivation. And all of this. And how I can actually convert all of this together, there are some algorithms for all of them. For example, if you have a parse tree, I'm claiming that you can write down a leftmost derivation as well. How to do it? Create your parse tree, then try to just traverse your parse tree in a depth first format, and whenever you reach to a node, so you might have actually more than one children, right? Visit the children in a left to right format, from the leftmost to the rightmost. Okay, this is going to give you a leftmost derivation. If you again run the DFS in your parse tree and visit all the nodes, but this time for each node visit the children from right to left, this is going to give you the rightmost derivation. If it is not clear for you, just draw a very simple parse tree and run the DFS over that and see that this is exactly going to give you the leftmost derivation or rightmost derivation. So this is another proof for this fact that yes, the leftmost derivation and rightmost derivation are equivalent. If it means that if you have a leftmost derivation, you definitely can write the rightmost derivation for that derivation as well. And if you have a derivation, how to create a recursive inference, just reverse the order of applying the rules. All right, these two are very intuitive. How to create a parse tree from a recursive inference? When you have a recursive inference in just a bottom-up way, you can create the tree from that. Or when you have a derivation, you can just in a top-down way create the parse tree. For example, look at this, that I have a grammar that's simple grammar that we wrote at first. And then a string like 0011, right? I can write down a derivation like a goes to 0a1, then 00a1, 1, and then 00 epsilon. A here goes to epsilon, right? And then 1, 1. I wrote one more. Okay, I can write down all of this derivation, convert it to a parse tree by just saying that, okay, if you read it in a form of derivation in a top-down manner, from A, you can create a tree like 0a1, right? And then get this one, replace A with that rule that you did. So the tree can be, and then replace this with epsilon. And that's it. This is the parse tree, equivalent to that derivation.